Hi everyone. Today let's talk about chapter 11. Session 11.1, differentiation. So chapter 11 is about numerical differentiation and numerical integration. So session 11.1 is differentiation and session 11.2 is numerical integration. Okay? Numerical differentiation requires us to find estimates for the derivative or slope of a function by using the function values at only a set of discrete points. So let me draw a picture here. Okay, so this is the f. Let's say we have some points here. And let's say this is xi, yi. This is xi plus 1, yi plus 1. And this is xi minus 1, yi minus 1. Okay? And in order to find the derivative at the points xi, well, that corresponds to the slope of the tangent line through that point, right? And then we can use secant line to approximate the tangent line. Okay. So here, use straight line to interpolate the data. We use 2-point estimates. We have the forward difference formula. So the derivative at the point xi, forwards means we're using the points and the next points. Okay, we look at the secant line passing through these 2 points and use the secant line slope to approximate the tangent line slope. Okay, so this guy is the secant line, so slope of the secant line. Okay, everybody? Yeah, you see it's change, this is change of y over change of x. So this is the slope of the secant line through those 2 points. And we also have the backward difference formula. So backward difference formula is, well, we're gonna take the points we have and we take the previous points. Well, then we find a line connecting them. This is the secant line passing through the points and the previous points. So this is the backward difference formula. And the central difference formula is we pick the next point and we pick the previous point and we calculate the slope of the secant line passing through those 2 points. Okay, let me see. So in this picture, Okay, so central difference formula is like here. These 2 guys. So these 3 different formulas is just based on which 2 points we select. The forward difference formula, we select the point and the next point. While the backward difference formula, we select the points and the previous points. The central difference formula, we select the next points and the previous points. Okay? So this is, we use straight line to approximate it, okay? And we can also use polynomial to interpolate the data. Okay, so how does that work? So polynomial, we know 2 points can fix a line. For polynomial, we need 3 points to fix the polynomial of degree 2, okay? So here we have the 3 points forward difference formula. Here we look at the 3 points. What are those 3 points? Okay, so let me draw the picture here. So this is xi, yi, xi plus 1, yi plus 1. Here, xi plus 2, yi plus 2. Okay? And we have xi minus 1, yi minus 1, xi minus 2, yi minus 2. Okay, so the let me use a different color. Okay, the 3 points forward difference formula, we can use the forward. So it's the points and the next 2 points to calculate. Okay, and then we can generate a polynomial passing through those 3 points and use the information to approximate it. Okay, and this is the formula. the 3 points backwards difference formula, we use the points and the 2 previous points. So we use this guy, this guy, this guy to generate a polynomial to approximate it. So far, so good, everybody? Okay, example 1. Use the following points to estimate it. F prime of x2 equals f prime of 3. Okay, so let's see. If we want to use the forward difference formula, because here we have 5 points and we're interested in f prime of x2. The forward difference formula includes the points and the next point. Okay, and we want to calculate the sum of the secant line passing through those 2 points, which is the change of the y coordinates over the change of the x coordinates. So that's why here we get f of 4 minus f of 3 over 4 minus 3. And f of 4 equals 16. F of 3 equals 8. 4 minus 3 is 1. So the answer here is 8. So far, so good? Okay, how about backward difference formula? Well, we use the points and the previous points. Well, the previous points is x1, right? And we want to use the slope of the secant line passing through these 2 points to approximate the slope of the tangent line. And so here we have f of 3 minus f of 2 over 3 minus 2. F of 3 is 8. F of 2 is 4. 3 minus 2 is 1. So what is the answer here? That is 4. So far, so good, everybody? All right. Oh, by the way, in our formula, we use f of xi minus 1 minus f of xi, and we use xi minus 1 minus xi. Well, this is the same thing, okay? Because when you switch the top, you gain a minus. When you switch the bottom, you also gain a minus. So the minus cancel out. So it is the same thing. Okay, so here this is the same thing as you use f2 minus f of 3 and you use 2 minus 3. They're the same thing. Okay, so central difference formula, we use the previous points and the next points. So we have f of 4 minus f of 2 over 4 minus 2. See, change of y over change of x. F of 4 is 16. F of 2 is 4. And 4 minus 2 is 2. So 16 minus 4 is 12. 12 over 2. The answer is 6. So far, so good, everybody? Okay, now how about the 3 points forward difference formula? Okay, let me use a different color here. So forward difference formula, we need 3 points, including the points we're interested in, and the next 2 points. Okay, so we have the formula. We have the coefficient minus plus 4 minus 3. Okay. So this is minus f of x4 is 5 plus 4 of f of 4 and then minus 3 f of 3. Okay, we just plug into the formula. And then over x sub I plus 2 minus x up xi. So that is x4 minus x2. That's 5 minus 3. Okay, so 5 minus 3. Well, f of 5 is 32. F of 4 is 16. F of 3 is 8. All divided by 3. So 5 minus 3 is 2. Okay, what is that? Well, you know, 4 times 16 is 64. 64 minus 32 is 32. 3 times 8 is 24. 32 minus 24 is 8. So 8 divided by 2 is 4. The answer is 4 here. So far, so good, everybody. Okay, so how about the 3-point backward difference formula? Well, instead of the next 2 points, we use that point and the previous 2 points. And here we use 3 of f of that point minus 4 of the f of the previous point plus f of the previous 2 points. Okay, so 3 minus 4 and 1. 3 minus 4 and 1. Okay. So 3 is f of x2 is 3. 4 of x1 is 2. And next one is f of 1. Okay? And we use xi minus x of I minus 1, 2. So we use 3 minus 1. Okay, f of 3 is 8. F of 2 is 4. F of 1 is 2. 3 minus 1 is 2. Okay, what's that? Well, 3 times 8 is 24, minus 16 is 8. 8 plus 2 is 10. 10 divided by 2 is 5. Okay, so here we learned 5 formulas to approximate the slope of the tangent line at a point. So far, so good, everybody? Yeah, we just figure out the point and then find the correct formula and then just plug it in and calculate. Alright, let's continue. Okay, so the data are taken from the function y equals f of x equals 2 to the x. Find the derivative at 3 and compare with the above estimates. Alright, so how do we differentiate? Well, if you can remember, 2 to the x derivative is 2 to the x times ln of 2. So when we plug in 3, we get 2 to the 3 times ln of 2. Wow. What is that? So this is 8 ln of 2, and then that is approximately equals okay, so this is our calculator, and we use 8 times ln natural log of 2 equals 5.545177444. 177444. So far, so good, everybody? Yep, okay. So let's compare with our estimates. Well, okay. So, well, the forward difference formula is quite big, right? 8. And what's the shape of this guy? 2 to the x exponential function is something like this, right? And you can see the slope is getting bigger. And our answer is 5.545, right? So somewhere near between 4 and 6. So these are the closers, and 4 is also closer. And the closest is this 5 and this 6. Okay, but they're approximation. Okay, if the points we pick are closer to each other, then the approximation will be closer. Okay. All right, let's continue. Example 2. Let f of x be e to the x times square root of x squared plus 3x. Complete the following table using the 2 points forward difference formula. Okay, approximation. Here we want to calculate the approximation and the absolute error. So far, so good, everybody? And here we want to use the 2 points forward difference formula. What does that mean? Well, it means that we want to, for xi, that is approximated by the xi plus 1 minus f of xi over xi plus 1 minus xi. But in this case, h is the step size. Okay, so which means here, let's say we have a point here. This point is xi. This point is xi plus 1. Then the difference between them is h. Okay, h is the step size. So this is the same as saying this is f of xi plus h. Okay, minus f of xi all over the difference between them is h. And so in our example, we're calculating the we want to approximate f prime of 1. So we plug in xi is 1, we get 1 plus h f of 1 over h. So this is the formula we're gonna use. And let's plug in when h equals 0.1. Well, f1 is approximately by f of 1.1, right? 1 plus 0.1 is 1.1 minus f of 1 over 0.1. So far, so good, everybody? Okay, what is that? Well, which means we plug in e to the 1.1 and then square root of 1.1 squared plus 3 times 1.1. What is f of 1? Oh, actually, what is f of 1 we can calculate here. F of 1 is e to the 1, and then square root of 1 squared is 1, plus 3 times 1 is 3. 1 plus 3 is 4. Square root of 4 is 2. So this is just 2e, right? And then over 0.1. Okay, let's plug this in our calculator. Okay. So how do we plug it in our calculator? Because you kind of expect here we have different step size. So then in order to like make use of the equation and save us some work. So when you type in, I suggest you type 1.1 and then click enter. And then use the answer, okay? So we have e. So e to the answer times square root of answer square plus 3 times the answer. Okay, this guy minus 2e. E is like e to the 1. Okay, you can do e to the 1 there. And oh, we forget the parentheses. Yep, we need the parentheses. Everything divided by 0.1. Is that okay, everybody? Do you see how I write it in our calculator? Okay, so when we click enter, we get 9.433 118029. 9.43311 and then what? 8029. So far so good, everybody? Okay, what if we change the step size to 0.5? Well, f prime of 1 is approximately by f of, see, this is 1.05 minus f of 1 over step size is 0.05. And what do you change? So you replace 1.1 by 1.05. So 1.05 squared plus 3 times 1.05 minus 2e over 0.05. So far so good, everybody? Alright, let's look at our calculator. This is the good thing about why we type in answer, because now we just need to type in 1.05, and then when you do enter, then you go back to the previous line to copy this equation. And what you do with your actual calculator, you just click, go back to the line, and then you will see this equation. But be careful, you have to check it. So e to the 1.05 square root of 1.05 squared plus 3 times 1.05 over 2 minus 2e, but over, not over 0.1. It's over 0.05. So this is the place you need to change. Okay? So be careful when you go back to the line and enter it. It saves you some time to retype the whole formula, but you have to check it carefully what number you're gonna change. Okay, so here our answer is 9.127349886. 9.12734 and then what? 9886. 9886. Okay, are you able to like read off the whole list of the number and then you can write it down at once? I can't. I can't. Maybe I can just remember the 5 numbers, but the long 10 numbers I can't remember it. Can you do it? Oh, right. So this is step size 0.05. So yeah, I really hope that all of you can get more practice. So please pause the video here and then try to complete the example. Okay? And after you're done, you can continue to play the video and check your work. Okay, sometimes I forgot to say that, but please, before we do each example, try to do it first. Okay? And then continue to play the video and check your answer. Then you can have more practice. So what do we change here? So instead of 0.05, we have 0.025. This is the f of 1. This is 0.025, right? Yeah, in the exam, you're gonna show all of these work. Okay? Because then you will get a lot of partial credits. Sometimes, you know, in our course, we work with a lot of small numbers. If we forget to change one spot, we get the wrong answer. If you don't show your work, then it's just a wrong number to me. How can I give you points? But no, if you write down more steps, I can give you partial credit. I know you understand the steps and the concepts, but you just make some algebra mistakes. So I can give you partial credits. So far, so good, everybody? All right, let's see. Okay, so we changed number to 1.025, and then you click enter, and then you go up to the previous equation, copy it, and then what do you change now? You see, at the bottom, we changed to 0.025. And the answer is 8.97931, 8.97931, and then 2051. So far, so good, everybody? Okay, and then we also, so these are our approximations. But what is the absolute error? Well, absolute error means we have to find the actual, the true value. So what is the true value? Well, it means we have to differentiate. Let's differentiate this guy, right? This is product, so we use product rule. Okay. Let me copy down this guy here. Then I don't need to go back and forth. So here, let me move to the left. Okay, good. So what is the derivative? Well, product rule, we have f prime of x. Well, that is the derivative of the first guy times the derivative of the second guy. For the second guy, I want to rewrite it as this guy to the 1/2. Okay? And actually, we don't need parentheses here. Okay, plus the first guy times the derivative of the second guy. Okay, so this is just product rule. Let's do it step by step. Derivative of e to the x is e to the x. And we have x squared plus 3x to the 1/2 plus e to the x. Well, this guy prime, chain rule, right? U to the 1/2 is 1/2, and then u to the minus 1/2 times u prime, right? That is chain rule. And let's see, this is e to the x, and then x squared plus 3x to the 1/2. And then here, what is this guy prime? Well, it's just 2x, right? And the 2 and the 2 and the 1/2 cancel. So we have e to the x, and then x squared plus 3x to the minus 1/2. And then there's x there. So far, so good, everybody? Oh, I make a mistake. No, I can't do that. Because the derivative is 2x plus 3. Then I cannot cancel the 2. So 2 stay there. And then here we have 2x plus 3. Yes, sometimes we have to be careful and check our work. Okay. Yeah, so you can see sometimes even I make mistakes. But it's okay. We learn from our mistakes. We just need to be careful and check our work. Okay? Alright, so we want to plug in 1. E to the 1 is 1. 1 squared is 1. 3 times 1 is 1. 1 plus 3 is 4. Square root of 4 is 2. E to the 1 is e. And then this guy, 1 squared plus 3 is 4. 4 to the negative 1/2, this is like 1 over square root of 4. So this is 1 over 2. And then 2 plus 3 is 5. Okay, let's see what this is. Well, we can factor out e, and then this is like 2 minus 5 over 4. You know, 2 is 8 over 4. So this is 3e over 4. And, oh, why do I have it minus? See? I have a mistake again. Gotta be very, very careful. So then we have 8 plus 5 is 13. 13e over 4. Calculator. 13e. So it's like e to the 1. And then go back down over 4. Okay, so the answer is 8.834415942. 8.83441. 8.83441. 5942. So far, so good, everybody? Okay, now, what are the absolute error? Well, absolute error, let's look at the first approximation. Well, that is 9.433118029 minus 8.834415942. Okay, what is that answer? Let's see, can we go back and find that number? Then we don't need to type it again. Yep, it's right here. So this guy minus our previous answer. Okay, so we get 0.598702085. 0.598 and then what is that? 7020. And then what is that? 865. So far, so good, everybody. Okay, next, for the step size, h is 0.05. Well, then we change this number by 1.127349886 minus this our true value. And what is that? And let's write it down. For the step size 0.25, we have 8.979312051 and minus this the same number. So far so good. Okay, let's put this in our calculator. Okay, let's find that number 9.127. Okay, this guy. We copy down here minus the true value here. Okay, so 0.2929 and then 33944. Oh, 0.2929 33944. Is that right? Yep. This number is easier to remember. Okay, next we have the 8.97, this number. Okay. And then minus that. 14486. 0.14486. And then, oh, it's 896,109. 896,109. So far, so good, everybody. Okay. So this is how we approximate the slope at a point. Okay. And you can see here we use the 2 points forward difference formula. It will be a good exercise for you to compute, to redo this example using the 2 points backward difference formula, or you can also use the 2 points central difference formula. So far, so good, everybody? Okay, so please redo this exercise at home using the 2 point backward difference formula or the 2 point central difference formula. Okay, next. Oh, so we talk about approximation. Then next, let's talk about the error. Right? Error tells us like how good the approximation is. Okay, the forward difference formula can be found from the Taylor polynomial with the remainder. Okay, so this is the Taylor polynomial. Okay, and so let me recall you what is the Taylor polynomial. So we have f of x equals to f of a, and then f prime of a x minus a plus so if you want to have this guy equal, okay, if you just want to keep here we have two terms of the Taylor polynomial, then for the last term, for the remainder term, you need to replace a by eta, where eta is some number between a and x. Okay, so eta is between a and x. Okay, so this is the Taylor polynomial. And this guy is the remainder. Okay, now how we change it? We plug in. Okay, so we plug in x, and we replace x by x plus h. And for a, we replace a by x. Now what happened? Well, this guy x, we plug in x plus h. Then we have this a, we plug in x, and f prime of a become f prime of x. Now what is h? You can see x minus a is just x plus h minus x. They cancel out. It's just h. So x minus a become h. So far so good, everybody? And then so this is h squared over 2, and then f prime prime of eta. Okay, so we get this from the Taylor polynomial with remainder. All right. So if we let h be xi plus 1 minus xi, then we get this formula. Wow, look at this. This is exactly the forward difference formula. Okay, and this is the error. The remainder term is actually the error between them. Okay, so the truncation error for the forward difference formula OH means this is the degree of H is 1. Okay, so it's degree 1 error. So far so good, everybody? Okay, and usually if the degree of the error is higher, then the error is smaller. Okay, so if let's say if we have OHN, if N is higher, then the error is smaller. Why is that? Think about your error when your approximation is getting closer, so your error is smaller. Think about it. If H is 0.1, then H squared will be 0.01. See? This error is smaller if the degree of H is bigger. Okay? Oh, right. So, and if we let H be xi minus 1 minus xi, then we get the backward difference formula. Okay, so this is the backward difference formula, and this is the error. Okay, so this is the error. Okay, so this is the backward difference formula, and this guy is the forward difference formula. Okay. So the error is also a first order error. Okay. The central difference formula can be found from the following two Taylor polynomial with h is xi plus 1 minus xi and equals xi minus 1. Well, in this case, you can see let's keep 3 terms in the Taylor polynomial. So the remainder, okay, here the remainder is a degree 3 in H. Okay? Alright, so now compare these two formula, okay? So let's see. Okay, how do we get this? Because look at the first one, f of xi plus 1 is f of xi plus h, right? And we have this formula. We just insert one more term at the end, okay? And then now you can see the h squared and h cubed there, okay? And then the bottom formula, okay, we can simply just replace h by minus h. Okay, we place h by minus h, then this guy become h, but minus h squared is positive, so that's why this is positive and this is negative. So far so good. But the thing we need to be careful is this eta 1, this eta 2, they are different things. Okay, for the remainder we get the eta is some number between x and a. Okay, but here because we have two different equations, the eta can be different. Okay, they might not be the same, so you cannot cancel them when you add those two equations together. Okay, so if we subtract those two equations together, and you see f of xi cancel, we have 2h f prime xi, and this guy also cancel, the second derivative cancel. Now we have this is the h cubed terms. Okay, and so far so good, everybody? Alright, now we can use the intermediate value theorem to replace the average of the third derivative at the unknown points eta 1, eta 2 by the third derivative at one unknown point eta in the interval. Okay, that is by intermediate value theorem. Now, we can solve for f prime. Okay, how do we solve for f prime? Well, we can move the other terms to the other side, and then we can divide it by 2h. right? Well, this guy moved to the other side is like is like negative h cubed over 3 factorial f prime prime eta when we divide it by 2h. Okay. Oh, so actually when we divide it by 2h, it's 3 factorial times 2. So 3 factorial is already 6. Okay, so alright. What happens is here, okay, let me write down the detail. How do we get this? Okay, so by intermediate value theorem, we know that, okay, so we have two values, f prime 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 of eta 1 and f prime 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 of eta 2, right? And let's say the middle value of it is like f prime prime eta 1 plus eta prime 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 of eta 2 divided by 2. This is like the average of them, right? Intermediate value theorem tells us that if we have 2 points, let's say this is x, and then this function y equals triple derivative of x. Okay, and here we have eta 1, here we have eta 2. Okay, then let's look at the average value of them. The intermediate value theorem to say that for any values that's between those two numbers, okay, f prime 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 of eta 1, f prime 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 of eta 2, there must be a point between them, let's say eta, such that the function applied on this eta equals to that value. Okay, so that's why here we get f prime 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 eta 1 plus f prime 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 eta 2 is then 2 times f prime 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 of eta. Okay, so that is why, okay, those two terms is the same as h cubed over 3 factorial is 3 times 2, but because f prime 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 eta 1 plus f prime prime eta 2 is 2 times f prime 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 eta. So when you multiply by 2 f prime 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 eta, well, the 2 and 2 cancel out. So that's why we only have h cubed f prime 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 eta over 3. Okay, and we can move it to the left, and when we divide it by 2h, now we get h cubed become h squared, and then we have f prime 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 eta over 6. So this is how this 6 come from. Is that okay, everybody? Alright, and now we can see this is our central difference formula. Okay, this is the central difference formula. And this is the error. And can you see now the error is a second order error. So because a second order error, it means in general this central difference formula is more accurate. Okay? Than the 2 points forward method and the 2 points backward methods. So far, so good, everybody? Okay. Well, for higher derivatives, then we're gonna consider more terms in the Taylor polynomial. Okay, for example, if we want to calculate the second derivative, well, first we consider the Taylor polynomial, and let's keep 4 terms in the Taylor polynomial, and then here is the remainder. So far, so good. And we can consider the previous point, which is xi minus h. Simply is the same formula, just replace h by minus h. Then this is negative. Minus h squared is still positive. And then this is negative, but this is still positive. So far, so good, everybody. Now, add those two equations because we want to approximate f prime prime. So we don't want f prime. We add them, then we can cancel out f prime. Okay, so on the left, we have f of xi plus 1 plus f of xi minus 1. And then here we have 2 of f of xi. And then here the f prime cancel. Okay, and here, what do we get? So this guy, 1/2 plus 1/2 is 1. So that we have h squared f prime prime of xi. And then here they cancel. You see, actually the odd degree terms, they cancel. Okay? And at the end, for the remainder, this is the remainder. Okay? And when we solve for f prime prime, how do we do it? We can move the 2fxi on the left and move this arrow term to the left, and then we divide it by 2. Oh, sorry, we divide it by h squared. So that's why you have f of xi plus 1 minus 2f of xi plus f of xi minus 1 divided by h squared. And you can see this arrow, when we move to the other side, it becomes negative. And when we divide it by h squared, well, h to the 4th now become h squared. So far, so good, everybody? And you can see, because it's h squared, this is also a second order error. Okay? And this is the central difference formula for the second derivative. Okay. And it needs 3 points. So for the first derivative, we just need 2 points to approximate. For the second derivative, we need 3 points to approximate. For the third derivative, we're gonna need 4 points, etc. So here I provide you the central difference formulas for first derivative, second derivative, third derivative, and the fourth derivative. Just play with the Taylor polynomial and of more points. Okay, and do some calculation. And all of them are second order error. Okay, so all of them are second order error. So far, so good? Okay, and we mainly use these twos. Okay, we mainly calculate the derivative and the second derivative. So far, so good, everybody? All right, next, let's do some example. Okay, let's look at the following example. We have x squared e to the x completes the following table using the central difference approximation of f prime prime of 1. Okay, so let's figure out what the formula gonna change. Alright, so f prime prime of xi approximately by f of xi plus 1 minus 2 of f of xi plus f of xi minus 1 all over h squared. Okay, and here we have 3 points. We have xi, xi minus 1, xi plus 1. And the difference of them are also h. H is still the step size. So that's why here xi plus 1 is actually xi plus h, and xi minus 1 is actually xi minus h. Okay, so because here we are looking for f prime prime of 1, so we plug in xi is 1, then we have f of 1 plus h minus 2 f of 1, and then plus f of 1 minus h, all over h squared. So far, so good, everybody? So this is the formula we're gonna use in our example. So next, we're gonna plug in our example. So first, h is 0.1. Then the second derivative is approximately by f of 1.1 minus 2 f of 1 plus f of 1 minus 0.1 is 0.9 all over 0.1 squared. Okay, what is that? Well, 1.1, well, we plug in f, x squared, so 1.1 squared, and e to the 1.1. Minus 2, okay, let's figure out what is f of 1. Well, x squared, 1 squared is 1, and then e to the 1 is e, so the answer is just e, okay? And then we have plus f of 0.9, so 0.9 squared, e to the 0.9, all over 0.1 squared. So far, so good, everybody? Okay, now let's see what this number is. So our calculator, we do big parentheses 1.1 squared, and then e to the 1.1, oops, and then come down here, minus 2e. So e is like e to the 1. Come down, plus 0.9 squared. And then e to the 0.9. Okay, close it and then divide it by 0.1 squared. Okay, double check our inputs. That's right. So enter. The answer is 19.7557521. Okay, so 19.07557 and then 521. So far so good, everybody? Okay, how about when h equals 0.05? Well then, what's gonna change? Well, this is 1.05. This is still f of 1. This is f of 0.95. The bottom is 0.05 squared. So what do we change? 1.05 squared e to the 1.05 minus 2e plus 0.95 squared e to the 0.95 all over 0.05 squared. So far so good? Okay, so it's very similar to the previous formula, but what we need to figure out is what's gonna change, which number is gonna change. Okay, so we can copy the previous formula here. Okay, and then what do we want to change? Let's modify it. So we change to 1.05. This is 1.05. And this is 0.95. This is 0.95. And the bottom is 0.05 squared. Okay, so the answer is 19.0398. And then we have 6731. Okay. So far, so good, everybody? So we still have the last step size. Okay. This is smaller. You can see the approximation is gonna be better. And how do we change? Okay, so this is, we just insert. Well, this is 0.975, right? And then 0.025 squared. And how do we change? 1.025 squared e to the 1.025 minus 2e 0.975 squared e to the 0.975 all over 0.025 squared. Is that okay, everybody? Alright, let's continue. So we copy the previous line. So we don't need to input the whole thing again, right? Just modify it. This is 1.025 and this is 0.975. See, we just insert, modify a little bit, 0.025, and enter 19.0309, and then what? 4605. So far, so good, everybody? Okay, so those are the approximations. Next, let's calculate the true value. So what's the true value? It means we have to differentiate this guy. Okay, we need to find the second derivative of it. This is x squared e to the x, so not that bad, right? So x squared e to the x. First derivative, product rule, x squared prime e to the x plus x squared e to the x prime. X squared derivative is 2x and e to the x. X squared e to the x derivative is e to the x. And then for the second derivative, product rule. So 2x prime e to the x plus 2x e to the x prime. But the second term, we also need to use the product rule. But do you realize the second term is our f of x? And we already calculate the derivative of it. And it is 2x e to the x and x squared e to the x. Okay, so derivative of 2x is 2 e to the x. And then e to the x derivative is e to the x. So let's just copy down here. So we have 2e to the x and then 4x e to the x and x squared e to the x. So far, so good. And we want to plug in 1. So it's 2e plus 4e and 1 squared is 1e. Oh, 2, 4, 1 is 7e. What is 7e? Okay, let's see. Calculator 7e. $19.0279728. Do I miss something? Let me see. Okay, 19.0279728. Yay, that's right. Okay, now, so this is our true value. And then now we want to compute the absolute error of each approximation. So absolute error. Okay, the first one, we use 19.07557 sorry, this is 521 minus our true value 19.079728. And what is this number? Why don't we copy down everything and then we can do the calculation at one time, right? 039866731. This guy, we copy it. The third approximation, 19.0309465. 19.0279728. Okay. What are these numbers? Calculator, where are you? Here. So we find the approximation. This is the number. Oops. Okay. We copy it. Minus our true value is this guy. Okay, so the answer is 0.0476. 0.0476. And then 0241. So far, so good, everybody? Okay, the second one, let's find it. 398 here. So copy down here and then, all right, enter. 0.0118941. 0.01198, right? Oh, 89. 451. 89451. Okay. And the last one. Let's go up again. 19.0309. Okay, this number. And then okay, 0.00297, 0.00297, and then we have 325. Okay, you can see that our error is smaller. Okay, everybody? Because the step size is smaller, then the points are closer to each other, then the approximation will be better. Okay, and so if you redo the previous example using the central difference formula, and you will see the error is also smaller. And why is that? Because the forward difference formula and the backward difference formula, the error is first order error, okay? But the central difference formula, the error is second order error. So in general, the central difference formula should be more accurate than the other two methods. So far, so good, everybody? Alright, so we will continue in video part B. See you soon!